Hey friends, welcome back. Today we are going to understand one of the most important concepts in backend engineering and system design, database sharding. And trust me, this is the concept that helps apps like Instagram, YouTube, Facebook, Netflix, and many massive platforms scale to billions of users. Because think carefully. What happens when one database becomes too big? Too many users, too many reads, too many writes, too much traffic. Eventually, one database machine cannot handle everything. And that is where scaling problems begin. So today we'll understand what sharding actually is, why normal databases fail at scale, how sharding solves the problem, what partitions really mean, what user-based sharding means, what hot shards are, how requests move internally, and how companies design these systems in production. And don't worry, we'll understand everything step by step, deeply, but very simply. So let's begin. First, let's understand the real problem. Imagine you build a small social media app. Initially, everything works perfectly. You have one backend server and one database. Simple architecture. Now suppose first 100 users join. Easy. Then 10,000 users. Still manageable. Then suddenly, 1 million users arrive. Now things become harder. Users upload photos, likes increase, comments increase, messages increase, feeds refresh constantly. And suddenly, your single database starts struggling. CPU usage increases, memory usage increases, disk reads increase, disk writes increase, database connections become overloaded, queries become slower, users start facing delays. Now many beginners think, just buy a bigger server. And yes, initially that works. This is called vertical scaling, meaning increased power of same machine, more RAM, more CPU, faster SSD, better hardware. But eventually, even biggest machine has limits. You cannot scale vertically forever. At some point, one database machine simply cannot handle billions of users. So companies needed another solution. And that solution became horizontal scaling. Now, instead of using one giant database, what if we use many databases? Think of it like this. Suppose one restaurant becomes overcrowded. Instead of making one giant restaurant, you open multiple branches. Traffic gets distributed. Same thing happens in distributed systems. Instead of storing all users in one database, we divide data across multiple databases. This is called sharding. Now many beginners hear terms like partitioning, sharding, distributed database, splitting, and get confused. So let's simplify properly. Partitioning simply means breaking large data into smaller pieces. That's it. Suppose one table has 1 billion users. Instead of keeping everything together, we divide data into smaller sections. These smaller sections are called partitions. Now partitions can exist inside same database or across multiple servers. When partitions are distributed across multiple machines, that becomes sharding. Very important difference. Partitioning means splitting data. Sharding means distributing partitions across multiple servers. Now let's understand real sharding. Suppose Instagram has billions of users. Can one database store everything efficiently? Very difficult. So Instagram may divide users like this. Users 1 to 1 million go to database A. Users 1 million to 2 million go to database B. Users 2 million to 3 million go to database C. Now traffic gets distributed. Storage gets distributed. Queries get distributed. Load becomes smaller per machine. And scalability improves massively. Each database becomes a shard. And this entire process is called database sharding. But now another important question appears. How does system know which user belongs to which shard? Because otherwise request routing becomes impossible. And this introduces another important concept. Shard keys. Shard key decides how data gets distributed. And choosing correct shard key is extremely important, because bad shard key can destroy system performance. Now suppose we choose user ID as shard key. System may calculate something like user ID mod 4, meaning divide user ID by number of shards, and remainder decides destination shard. Example, user 101 goes to shard 1, user 102 goes to shard 2, user 103 goes to shard 3, user 104 goes to shard 0. Now data spreads evenly. This is simple hashing-based sharding. And yes, real systems use more advanced strategies. But core idea remains similar. Now internally, whenever request comes, application first calculates shard, then request gets routed to correct database. So internally, architecture often looks like this. User request, backend service, shard router, correct shard database. And this routing layer becomes extremely important in distributed systems. Now let's understand one very common strategy, user-based sharding, meaning all data related to one user stays together. For example, user posts, messages, followers, likes, settings, everything related to user 101 may live in same shard. Why? Because most queries become easier. Suppose Instagram opens your profile. System already knows your shard, so related queries become faster. This improves locality and reduces cross-shard communication. Now this sounds amazing, but distributed systems always create new problems. And now we hit another major issue, hot shards. Now imagine one normal user and one celebrity user. Suppose celebrity has 500 million followers. Suddenly, one shard receives massive traffic, while other shards stay mostly idle. This creates imbalance. One database becomes overloaded. This is called hot shard problem, meaning some shards become extremely busy compared to others. And this becomes a huge challenge in distributed systems, because equal data distribution does not guarantee equal traffic distribution. Very important engineering lesson. Now companies solve this using techniques like better shard keys, traffic splitting, caching, replication, dynamic resharding, and load balancing. But yes, managing hot shards becomes difficult at massive scale. Now another important question. What if one shard crashes? Will user data disappear? That would be disastrous. So systems usually use replication, meaning multiple copies of same shard. Example, primary shard handles writes, replica shards handle reads. If primary fails, replica may become new primary. This improves availability, fault tolerance, reliability, and read scalability. Now architecture becomes more advanced. User request, shard router, primary shard, replica shards, caches, failover systems, monitoring systems. And suddenly, you realize how complex large distributed systems actually are. But now another problem appears. Suppose system grows massively. Initially you had 4 shards. Now traffic becomes huge. You need 20 shards. How do you move data safely? This process is called resharding. And honestly, this is one of the hardest operations in distributed systems, because while moving data, system must remain online. Users should not notice failures. Queries should still work. Data consistency must remain correct. This requires careful engineering, background migration systems, traffic shifting, data synchronization, consistency checks, rollback systems. Large companies spend enormous effort solving these scaling problems. Now let's see final impact. Without sharding, one database becomes bottleneck. System eventually crashes under huge scale. But with sharding, storage scales, read scale, write scale, traffic distributes, and system handles billions of users. That is why almost every massive internet company uses sharding. Instagram, YouTube, Facebook, Twitter, Netflix, Amazon, Uber, almost everyone. Because modern internet scale simply cannot run on one database machine. But remember something very important. Sharding improves scalability, but increases complexity massively. Now engineers must manage routing, replication, consistency, cross-shard queries, resharding, hot shards, failures, monitoring, distributed transactions, and debugging becomes much harder. This is why distributed systems engineering is considered advanced backend engineering, because solving scale creates entirely new classes of problems. So today we understood why single databases fail at scale, difference between vertical and horizontal scaling, what partitioning means, what sharding actually is, how shard keys work, what user-based sharding means, what hot shards are, why replication matters, and why distributed databases become both powerful and complex. And honestly, this is only the beginning of distributed systems, because once systems become distributed, new challenges appear everywhere. Caching, replication, consistency, distributed locks, consensus algorithms, event streaming, fault tolerance, and much more. We'll explore those deeply in upcoming videos. If this video helped you finally understand database sharding properly, make sure to like the video, subscribe to the channel, and share it with someone learning backend engineering or system design. See you in the next one, where we make hard tech topics easy actually